All right, welcome back everyone to the final tutorial of the summer school. So just gonna get rid of that one message. Okay, it's being recorded. So far, what we've covered is how we can maybe come up with hypotheses and build models that provide computational kind of explicit commitments to computational processes for these hypotheses. And we've also kind of talked a little bit about how we can fit models to data. So the focus for the rest of okay. I think I just lost focus for my mouse. So the focus for the rest of this tutorial is to kind of determine which model is the best model, right? Finding some balance between model complexity and fit, and then also to kind of provide strong evidence that we can trust our interpretation of this model through robustness analyses. Okay. So that this tutorial has two main parts. We'll start with model comparison, and then we'll then move to a section on robustness that gives us kind of confidence that we can interpret the results from our model. So part one, model comparison. So in this sense, what we're trying to figure out is what makes a good model, okay? One kind of very common quote by George Box is that essentially all models are wrong, but some are useful, right? We're under no illusion here that our model is the truth in any situation, right? Models are never wrong, right? But useful models tell us something about the data that we couldn't understand in its raw format through the kind of simple behavioral analyses alone. And ultimately, one good kind of rule of thumb is that we want our model to be as simple as possible, but no simpler. So this is one really great short story by Jorge Luis Borges about an empire that created a map exactly the size of the empire. That's one-to-one a map for the empire. So this is kind of a fable that kind of illustrates the kind of the absurdity of making a model that's absolutely perfect, that matches one-to-one in complexity to the target that it's trying to capture, right? And this map of the empire is absolutely useless, right? It frays at the edges, it is kind of destroyed by the sun and by the weather, right? We make maps that provide us a kind of helpful, we make maps to be useful, to help us guide our planning and our route finding, and that involves removing a lot of details that are not relevant to our actual kind of the purpose that it serves, right? And for the same way, we build models that need to kind of eliminate a lot of the complexity to focus on the main phenomena that we care about, right? So our models are not trying to be perfect, they're trying to be useful. And so one kind of way to capture this is kind of very simple regression models. So that's a very kind of simple case here. So we might be trying to kind of model the kind of the cyclical change in temperature. So here's the daily temperature in London as a function of the day of the year, temperatures on the y-axis. And we might kind of consider two different types of regression models of different levels of complexity, right? So a polynomial of degree 3 is indicated by this dashed line. So that's relatively simpler than a 12-degree polynomial, which has all these kind of curves in this line. And on the right here, we can kind of see how good of a fit these different models provide, right? So as we increase the degree of the polynomial, we see that the error of fitting kind of continues to decrease over time, right? As we get more and more complexity. But it's really that when we're looking at predicting, right? Predicting out a sample, right? New data that we're not fitting to, that as we get more complexity, initially the predicting error decreases, but then starts to gradually increase, right? And rapidly gets very, very large. So ultimately, what we're trying to do is to find some balance in complexity that balances both our ability to fit the data while also ensuring that we can capture some general principles that also allow us to predict at a sample, right? So this is kind of this like tug of war that we have to play between simplicity and fit. And most approaches to model selection operate by providing some way to balance these two kind of opposing forces. Good. And today we're going to present kind of a rough overview of different goodness and fit measures. I've roughly kind of arranged them based on these columns, where some approaches are based on a maximum likelihood approach. This is kind of the single point estimate, the like what is the argmax, right? What is the best fit versus Bayesian model selection, which operates over kind of probability distributions. So that's the theory, but in practice, I've also arranged these in two different columns, where in practice, we can have an approach that kind of has an explicit penalization for parameters. And across both maximum likelihood and Bayesian interpretations, there's very similar approaches. So based on AIC and BIC. And then there's other approaches that kind of use kind of prediction error or as a form of kind of Bayesian's Occam razor. So we can do things like cross-validation, or we might do MCMC sampling, which Joe introduced this morning. So we'll walk through all of these, and I think we're going to start with just kind of the theory behind these kind of two different frameworks, okay? So maximum likelihood estimation, right, like we kind of showed in the previous tutorial, is trying to quantify the goodness of fit for a single set of parameters theta hat that provides the best fit for the data. We're trying to get some argmax over these parameters, right? So given a model M, we want to find the theta hat that gives us the best fit for the data. We illustrated this in the tutorial 2. And in this situation, overfitting is typically avoided by penalizing for the number of parameters, like using AIC, or using something like cross-validation to test for predictive power. In the Bayesian framework, what we're trying to do is we're trying to figure out, okay, not only are we trying to value the model at its best, we also want to kind of capture the model across the entire range of parameters, theta, right? So we're trying to capture something about what's known as the marginal likelihood, right, where we're integrating over the entire space of parameters. We're not only capturing the model at its best, but also at its worst. And this allows us to kind of capture some sort of more natural penalization for the model, right? So overly complex models, in this case, maybe in this best situation could provide the best fit, but in general, it's overly complex, and from one situation to another, it might not actually be the best best model, right? So the basic idea between this is that we're testing the model at its best. We're also here, we're testing the model across the entire range of parameters, also when it's at its worst, okay? But this formulation is typically intractable mathematically in most settings, right? So we often have to approximate this using things like BIC or MCMC sampling, okay? So for any interesting models, almost any continuous sets of any continuous parameters, this is intractable. Good. So we're going to start with kind of this first simple approach, which is based on penalizing for parameters, and then we'll move on to the kind of the other sets of approaches afterwards. Good. So I think I saw a bunch of posters with AIC on them as a means for model comparison. And this is really one of the most simple approaches. So AIC is simply taking this, what we call the deviance, right? So -2 times the log likelihood at the maximum likelihood estimate. So this is capturing the fit, right? So how good is the model? And we're essentially just doing kind of this. You're taking your likelihood function, wrapping in an optimizer, and seeing what's the kind of the negative log likelihood at its best. And then here we add an additional complexity penalty, right? So remember that here, this is kind of a loss function, right? So the larger it is, the worse the model. And we add an additional penalty to models with more parameters, right? So we're adding 2 times the number of parameters. So K is the number of parameters here. Right, so we're simply penalizing for parameters. In that kind of simple example I gave you earlier about the kind of polynomial regressions, we would then choose something with a smaller degree of polynomial rather than the higher ones because we're not getting better fits. So what is the theory behind AIC? Okay, this is kind of abstract, but I want to gesture at this a little bit. So AIC is trying to capture some measure of the relative information lost by a given model that's trying to capture some objective reality Rx. So of course, we don't know what this objective reality Rx is. Imagine kind of in some kind of abstract space, there's some reality of the data and there's a bunch of models. And then AIC is kind of trying to capture kind of how much reality is lost or how close we get to this reality at this argmax, right? So this curve here represents kind of the different kind of predictions made by this model 3 at different values of theta. And this closest point is theta hat, okay? And so this is kind of capturing some sort of difference between the reality and the model at its best. Okay, very abstract. We never have access to R. But in practice, asymptotically, so at the limit of infinite samples, AIC is actually equivalent to leave one out cross-validation, right? And this is true for linear regression and mixed effects regression. So general kind of general linear regressions, okay? And this is in the limit of infinite data, okay? So what is cross-validation? This is where we kind of iteratively take all of our data and we iteratively kind of leave one data point out, fit the model on the rest of the data, and try to predict on that test set, and kind of and repeat for different test data that we leave out, and we kind of add up the loss for all that, okay? So in this limit of infinite data and for linear regressions and mixed effects regressions, very limited class of models, AIC kind of has that interpretation, okay? But of course, we never have infinite data, and often people use AIC for other models that are not linear models, right? Reinforcement learning models, classifiers, etc. So in practice, though, right, so this interpretation is hardly ever met. In practice, AIC can be, though, rather considered the relatively most lax of the goodness of fit measures, right? So it doesn't penalize nearly as harshly as other forms of goodness of fit measures, right? So AIC compared to something like BIC or other measures is more likely to prefer an overfit model. You might end up having a more complex model win, even if it's not maybe justifiable according to other approaches, okay? Not to say that's bad. In some cases, it's totally fine to use this. I think definitely for the case of regressions, this interpretation actually makes it quite useful. So alternative approach in the more Bayesian framework is Bayesian information criterion. So you can see that that has a very similar formulation. You have the same kind of fit term here, which is our deviance term. And then here in the complexity term, it's formalized a bit differently. We still have k as a number of parameters, but then we kind of multiply this by log n, where n is the number of data points in our data. Okay, so just try to give you the kind of the theoretical interpretation of BIC. Bayesian model selection often relies on something called the Bayes factor as a way to quantify the evidence of one model over the other model. Okay, so it's the kind of probability of the data given model 1 or the probability of data given model 2. This is kind of the general kind of theoretical approach that Bayesian model selection is trying to take. And in this ratio, if this is equal to 1, so both models are equally good, right? There's no evidence for either model. When the Bayes factor is much larger than 1, when this kind of term, the numerator is much larger, we have more evidence for model 1 than model 2, then we have greater Bayes factors, and there's evidence for model 1. And when Bayes factor is smaller than 1, we have evidence for model 2. So BICs require some approximation of these two terms here, because these are the marginal likelihoods, recall, right? That requires integrating over an entire kind of range of parameter values. But of course, we can't do this. And BIC is a kind of an approximation of this marginal likelihood using maximum likelihood estimation and by making some theoretical assumptions about the prior, okay? So we can think about this BIC as being an approximation of this, and it's making some assumptions about the prior. Now, these, and this is just another way to write the Bayes factor as a function of the BICs. Now, these assumptions about the prior are hardly ever met, and this Bayesian interpretation is actually quite controversial, right? To what extent BIC actually captures these Bayesian principles of the marginal likelihood has a lot of controversy around it, and these assumptions are probably never met in any case that any of you have ever used BIC, okay? But in practice, though, we can think about the fact that BICs are generally more strict than AIC in penalizing for complexity. And BICs are then thus less likely to prefer an overfit model, right? And you can see this here. So this is the complexity term here, right? So note that how log of n is greater than 2 when there's at least 8 data points, okay? So when you're fitting a model on at least 8 data points, which I'm pretty sure almost all of you are, then BIC is going to be a harsher goodness fit measure for complex models, okay, and be less prone to overfit. Cool. So this is kind of the more practical interpretation of it, because the theoretical interpretation is rather hand-wavy at best. Good. Remember that we have these really great notebooks accompanying all the tutorials. Here, provide some code to kind of where you can simulate data from a Q-learning agent. So this Q-learning agent, I think it's a socially Q-learning agent. It has a number of choices here. It observes these other social choices above that informs this behavior. And here we're trying to fit the model based on Q-learning versus value shaping. And here I've kind of, each of these data points represents a single simulated agent. And here's the AIC and here's the BIC. And essentially the slope shows kind of which model is preferred. And in general, the Q-learning model is preferred because actually this is generated by a Q-learning agent, not a social learning agent. That's the kind of alternative hypothesis. Whereas the value shaping alternative has worse fit, and you can see by the difference in the slope that there's a stronger preference for the Q-learning agent in the BIC formulation, which is the simpler model, relative to AIC, right? So you can also maybe imagine some situation where the AIC makes errors in the other direction and accidentally prefers the more complex value shaping model that did not give rise to this behavior. Cool. So you can play around with that on your own time. Good. So we covered kind of this kind of very simple approaches for goodness of fit measures that work by penalizing parameters. And now we're going to move on to kind of cross-validation loss and model evidence using MCMC sampling. Cool. So I already talked a bit about cross-validation, where rather than trying to penalize for complexity post hoc, we can actively test the predictive accuracy of our model through cross-validation. And we do this by breaking up our data into separate training and test sets, right? So I've already introduced this idea of kind of cross-validation, where then we fit the model on the training data, and then we try to predict the test data, okay? And this goodness of fit can then be the summed negative log likelihood of all our edit sample predictions, right? So we kind of add up our loss across all these blue test data rounds, for instance, in this example. Okay, so the general approach to this is that kind of has an inner loop and an outer loop. So this inner loop is what we kind of talked about on the at tutorial 2, where we're iterating over our data. We maybe have some reinforcement learning agent here, trying to making kind of predictions about choices, and we're optimizing over this model to then get some theta hat, right? Some maximum likelihood estimate. Then we do this outer loop where we're iteratively kind of breaking up the data into training and test sets, fitting the model on this training data, and then we're then taking this theta hat and seeing how well it operates, how well it makes predictions on this out of sample test data. We do this for all the different slices of our data, and we sum this up to compute the cross-validation log loss. So there's a number of varieties of cross-validation. We can do this leave one round out cross-validation. So experiments often have multiple independent rounds that kind of allow us to kind of control for the different kind of dynamics of learning. I think in reinforced learning tasks, this is particularly important because a single round of data doesn't necessarily get you identifiable parameters like learning rates, etc. So we have multiple rounds, and that's kind of one of the best ways to kind of do this. We can also do k-fold cross-validation where there's no natural structure in the data. So a lot of times data is quite naturalistic, especially like spatial trajectories, and we can kind of break up the data artificially into some k number of different slices or k folds and do it this way. Or this extreme case is leave one out cross-validation, which is leaving a single data point out. And that's the AIC interpretation. But this potentially also doesn't necessarily work as well in reinforced learning settings where you kind of need sequential updates to kind of make good predictions. Good. Okay, so that's the kind of the maximum likelihood approach where you can use cross-validation to kind of directly test predictive accuracy. But then, as Joe already teased, there's a Bayesian approach that kind of lets us kind of get a better distributional understanding of how good our model is. So why would we even do this? Why would we add this additional complexity, right? So I think the basic difference is that rather than the maximum likelihood approach, which gets you single point estimates of the parameters, here we get a probability distribution over the parameters, okay? So this allows us to say that rather than assuming participants are these independent samples, we can also model them hierarchically as a population, right? We can get some population level estimates about what parameters exist in the world. And this maybe gets us a better way to kind of account for individual differences to get some overall effect of some manipulation. For instance, this is an example of one of my publications where we had people do a reinforced learning task under time pressure, and we see that time pressure influenced how much value-directed choices they made. There's a reduction in that along this scale. And here, these distributions represent the population level estimates of the parameters, okay? And additionally, one other benefit is that this Bayesian approach allows us to kind of naturally avoid overfitting through Bayesian's Occam-Brazer, right? Since we're evaluating the model across the entire range of parameters, we're also capturing them at not only their best, but also at their worst, okay? So previously, how do we get posterior distributions over parameters? So previously, we only used maximum likelihood estimate to provide a point estimate of our best parameters theta hats. And so here we want to estimate the full distribution of parameters suggested by the data and our choice of models, right? So this posterior is probability of our parameters theta, given the data and given a specific model. This is proportional to the likelihood, right, which is probability of the data given a single parameter set of parameters and the model, and then some prior over parameters and models, capturing some kind of our initial guesses before we see the data. And as Joe illustrated earlier, this is often done using Markov chain Monte Carlo, right? So the problem is that we want to model a probability distribution that's difficult to compute analytically, okay? And the solution here is to acquire random samples that approximate this distribution. So Markov chain Monte Carlo combines two different components. So the first is the Markov chain. So Joe illustrated this with a picture of Markov, right? That given the present, the past, the future is independent of the past. And here we essentially define a sequential process where each random sample is used as a stepping stone to generate the next sample. Okay, and this is kind of has a special property where the Markov chain has as this equilibrium distribution, the target distribution we're trying to approximate. And then the other part is the Monte Carlo that principle, that the law of large numbers, that enough randomly drawn samples will approximate the underlying distribution. Okay, so how do we do this? So what we're trying to do is figure out what our posterior probability distribution is. And we're going to start by sampling some initial kind of theta I from some proposal distribution. Okay, so this is how these kind of change over time, and often something very simple is like a Gaussian. And we'll compute the likelihood of the data given these parameters, this theta I. Okay, so that's kind of our initial sample here. Or sorry, let's say like we're at time I here, we're at this point here. Now we're going to accept the sample with the probability proportional to how much of an improvement it is over the previous theta I minus 1, right? Is theta I providing a better fit for the data or a worse fit for the data? Okay, so let's imagine we're in a situation here and we've sampled a theta I over here, and it's a much worse fit for the data. We're going to be much less likely to accept that. So we may reject it and then sample again, and maybe this is the sample that we accept. Okay, we still sometimes accept theta I's that are worse than the previous one, but we're much more likely to accept ones that improve. And this allows us over a kind of a sequential chain to then get some distribution over our samples that approximates our posterior. So this would then, histogram would then be our posterior. Okay, so here's an example of this MCMC kind of in action, right? We're getting these samples. This will kind of fluctuate between blue and I think red when it gets a rejection, which is a bit rare near the end. Yeah, here you can see a bunch of these red dots being rejections and green dots being acceptances. Okay, and so in the end, we're building this histogram, right, that captures our posterior. There's a number of different MCMC samplers you can use. So a common one is Stan, which is kind of built in R, and then the Python equivalent was PyMC. Again, there's no preference. Use the right tool for whatever setting you're using. But there is sometimes a bit of a steep learning curve. The way that we define models is based on kind of the relationships between different distributions to one another. So quite different maybe than the way we've taught you how to do modeling so far. But I have in this code notebook implemented a version of our simple Q-learning agent in Stan. I've simulated data from it, and I've estimated the model. And here's our kind of posterior over alpha, posterior over beta. And the dashed line is the true parameter estimates, right? So we get some noise around it, but more or less the mode is where the true values live. And so here you can kind of see an example of how to define kind of a Stan model for the simple Q-learning agent. And if you want kind of further reading, the 2023 iteration of Cosmos had a guest tutorial by Lei Zhang, and you can find the course materials online. And he provides a much more deep dive into modeling of Stan, including kind of other forms of information criterion that are more common in that domain, such as things like the WAIC, commonly called the widely applicable information criterion or the Watanabe Kake information criterion. And it's and here it's an approximation of this kind of leave one out prediction accuracy. Okay, so if you're interested in finding out more, there's some resources again available on our website. Cool. So just a kind of summary of part one. We have kind of two different kind of theoretical approaches to model to describing goodness of fit based on maximum likelihood or Bayesian model selection. But in practice, these you're more likely to kind of choose between an approach that penalizes for parameters via AIC or BIC, or by directly modeling the prediction error, or kind of going even further using MCMC sampling to get the full Bayesian model fits. We're going to round out this section with a model fitting exercise. So from the code notebook, you'll find links to download these two CSV files, meteor.csv and comet.csv. Along with it, we have some self-contained model fitting code that you can also use to then try to figure out which model best explains each of these data sets, right? So these data sets have trials, rounds, agent numbers. So you have a number of different agents across. So they're searching for rewards and they're making choices on a multi-round bandit, and the choice number is indicated here. Okay, and you should be able to kind of use this to try to fit and compare a number of models. We have an asocial individual learning model, just based only on individual information, a decision biasing model where the social information influences the policy, and a value shaping model where the social information influences the value function. So we're going to take a bit of time now to kind of let you get some hands-on experience with this. If you have any questions, I can walk around and we can kind of help debug a little bit. People having a hard time finding where the data sets are.
Basically, can like open up
Yeah,
the file
yeah.
and then copy paste.
Yeah, exactly. So if you're having trouble finding where the code examples are, sorry, it's hard to kind of for me to. I can't. It should be model fitting exercise. You can download these data sets, and if you press this code button, you can then kind of copy and paste this R code and use it in your own R environment to then do the model fitting. Should we maybe turn off this light here because it's kind of yeah, it's a bit harsh. Good. Yeah, I think that's better, right? feel like I should play some of your musical melodies over the sides. I think I have like 20, 30 minutes of content after this. But maybe also some time for discussion and questions.
Yeah.
Right, so then,
Maybe then
yeah.
wanted to.
Yeah. What we did last time? Didn't I ask like people to like guess? I forget what the right answer is.
Sorry?
I forget what the right answer is. Which model is that? Yeah, I don't remember anymore.
So we can, maybe people can run the model and then the estimating model.
Okay, so we can maybe pull people a little bit. Try that. Disagree.
Yeah. Yeah.
Because it was like
I can't remember actually.
Yeah, no, I don't know.
Codes like in you always reset the Q values
After every round, because you're learning essentially across rounds, these are these independent replications of the learning process, right? So every round is a new decision problem.
Yeah, but if you like just don't reset it, can it not like, do you think it's like kind of making it overfit then?
Well, it's going to affect the fitting. A couple of things there. So there's some sequential dependencies in learning, right?
Yeah.
The choices early on matter,
Yeah.
right? And so if you just keep going, you converge on a choice. You're not going to make any more stochasticity. Meteor, was it in the individual learning? Put your hands up. Decision biasing, value shaping. Okay, cool. And for comments, I'll go in reverse order. Value shaping, decision biasing, individual learning. Okay, so that one is a bit more mixed in the population, right? But I think it seems like most people got the correct answers. Anything that came up during the model fitting? Anything that you were unclear about? Any kind of decision nodes that maybe were a bit unclear? I had some chats with people asking whether or not you really had to fit models separately for each individual, or just pull the model of the data together. So, like for real participants, I generated this data where each virtual participant had a different set of parameters, right? So if you pull the data together, you're not going to get reliable model parameter estimates. Okay, and then related to that question, well, how do you think of the model fit, right? You don't get a single goodness of fit for each model, but rather for each participant. And then you can do things like doing a t-test to see which distribution, which population, right, which set of model fits for are better in the population, right? For model A versus model B. Okay. Any other questions or things that were unclear yet about kind of the model fitting and model comparison procedure that kind of became apparent during this exercise? Okay, so then maybe we can move on to the next section, which is this robustness. I think before we do that, maybe we'll have a quick 5-minute break, use the bathroom, and then we'll start again at 11:30. Okay. So I use the timers one. Okay, sorry. Yeah, but I think you just changed that. I don't think anyone had an issue
It's just like the how precise it is in encoding like comma separate.
Yeah.
Doesn't really make a difference.
But I should update that actually for the future, right? You have access to the website?
Yes, I do. You might no, I very happily will take that on board to buy. I had the yeah, but it's just like
Unless you're.
library. Actually.
But are you also on the I think I shared those on.
Maybe not.
That should be changed there. Like, I'm just like them. And then I copy and paste it. But I'll change that.
That was actually funny about the tutorial.
Very much our project we had bidding model, which is that when we look at like how listener variables we find like across time the first has learned what kind of speaker they're talking to.
I want to get people on that. All right, okay. So a lot of breaks on this last tutorial. Zoom recording? Okay. Great, welcome back everyone. So part two, I think this is one of my most kind of favorite parts of the tutorial, which is robustness. And I think it's a really important and kind of area for model computational modeling that is continues to develop in exciting ways. So I'm going to talk about three kind of forms of robustness checks because I think this is a way that I think computational modeling is kind of getting ahead of some of the types of kind of issues that other forms of behavioral science have been facing with replication crises, right? Where good robustness checks really allows kind of a computational modeling approach to kind of not just kind of be shooting into the dark with hypotheses, but rather making much more informed choices such that you don't really miss, right? This allows us to kind of already have some kind of confidence that before we run an experiment, we're going to have some results that distinguish between our hypotheses that we're interested in. So we're not just firing blindly. So we'll talk about three different types. So first of all, model recovery. This is kind of an analysis that lets us kind of test whether or not the data and the set of models, so whether or not the data and the nature of the experiment can actually differentiate between the models we are considering. Okay, because there can be model mimicry when the wrong model can mistakenly win. Okay, so this is a really important aspect of using models properly. Two is parameter recovery, and this is asking the question: are the parameters of the model capturing distinct and recoverable phenomena? Right? Can changes in one parameter path be commented by changes in another? And this would lead to problems of misspecification, such that we can't reliably assume that this parameter is really capturing the equivalent phenomenon. The two things are then being entangled together, right? And then lastly is simulated data. Can a model actually generate realistic participant behavior, right? Is it capturing the mechanisms that matter for performance? right? Rather than simply fitting the noise, right? Is our map actually useful? Okay. Good. So I'll start with model recovery. And this is something where I typically do for all my studies of models. And what we do is we typically start with some parameters that we use to simulate our model, right? This can be either a priori guesses if you haven't run an experiment yet, or our participant estimates, right, that we've gotten from our data. Okay, and we'll talk a bit more about this thing between the two a bit later. And then from these parameters, we simulate in the model, we simulate some generated data, and then we try to do estimation not only with that model but also our other models under consideration. Recall, we're trying to do very theory-driven work here using computational modeling, and we're kind of testing alternative hypotheses with these other models. So we're going to do some estimation, trying to see how good of a fit each of these models provide. Okay, so we're trying to use the kind of the same model estimation procedure as we're using for our participant data here, and this is key because the whether or not models will cover is a combination of the kind of the design of our experiments, the set of models under consideration, and our estimation procedure. Okay, so if you're getting some issues with model recovery, you might maybe change any of those three conditions. And so this is going to tell us how often does the correct model provide the best fit. So there's kind of often two common ways to assess the quality of these fits, and the kind of complementary approaches. And you can look at this great 10 Simple Rules paper by Rob Wilson and Ann Collins in Eli 2019. So the first thing we're going to show here is this confusion matrix. Show it this way. So the confusion matrix shows the probability that given a simulated model, that was simulated data from model 1, that the same model is also going to provide the best fit. Okay, so we're going to look at the rows of this matrix, right? So model simulated data simulated by model 1 is fitting 100% of the time. Okay, so these cells are indicating the probability that the best fitting model in some population simulations is for that simulated model that in the corresponding row. Okay, so in this situation, every single time, the best fitting model is the actual simulated model, model 1. But in some of these other rows, you have more problematic cases, right? So when we're simulating data for model 3, 54% of the time, model 3 is the best fitting model, which is still the highest, but a substantial amount of time, model 1 is actually providing the best fits of that. So it's mimicking, model 1 is mimicking model 3, leading to confusion. Okay, so this is already indicating some issues with this approach. Now, I think what is actually maybe more informative is what's known as the inversion matrix. So we're simply inverting this term using Bayes' rule. Okay, assuming some sort of prior over the simulated models. So here we interpret this along the columns, and this tells us that okay, given that a single model wins the model competition, like in our experiment, how likely is it to actually be the true generative model? Okay, and this accounts for the fact of this model mimic here. So in this situation here, model 1, so recall that this is kind of equivalent to this matrix here. Model 1 was really good at capturing itself, right? But it was also capturing a bunch of these other models as well, right? So it was overfitting other models. And so this inversion matrix reveals kind of some problems here that this confusion matrix maybe make this obvious that, hey, when model 1 wins, it's probably not all, it may not actually be the true generating model. A lot of the times, because it was overfitting these other models, the true model that simulated data was actually one of these other ones, right? So our participants could have been doing strategy 3 or strategy 4, but we're going to be mistakenly classifying them as model 1. Okay, so this is a really informative analysis here. And here's another situation which is much better, where model 5 is when that wins, we're able to reliably assess that it wins, right? And this looks quite different from over here, but that's because when model win, none of the other models really kind of overfit model 5, such that here we can be reliably confident that it is the true model. Okay, so model recovery can also be quite tricky when you have nested models. Right, so I've talked to someone about kind of having a bunch of different terms in their model that they want to test to see which ones are relevant. So often we'll lesion away components or gradually add them. So here's an example of some sort of model nesting, where model 1 has some number of parameters, model 2 adds additional parameter, model 3 adds additional parameter, right? And in these situations, it's very prone to model mimicry, right? Because when some of those parameters are kind of at very marginal small values, right, making small contributions to the actual predictions, then it behaves a lot like a simpler model. And for the nested models, not all ranges of parameters will then yield distinct behaviors. And so one analysis that I've been trying to kind of, I've been developing recently in this manuscript that's in prep right now, is that you can run model recovery over different parameter values, each new component, try to find ranges that have good recovery. So for instance, here's a situation where model 1 is as a baseline model and model 2 adds additional parameter, this kind of weight parameter here. And we simulated this new model 2 at different values of this weight, okay? And then we're running model recovery on that data against this model 2 and this baseline model 1. And what we're finding is that here we're getting some ranges where the probability of the best fitting model being equal to the simulated model reaches this kind of much better threshold for both situations, right? Of around 0.5, let's say it's somewhat arbitrary, in this range of parameter values. So we're going to select that, and we're going to use these as bounds for our estimation later, okay? And then similarly for a model that has even more parameter alpha, here again, we did some other equivalent analysis where we found for these values, we get good recovery. So this is a new analysis that I've been basically developing, but it's a common problem that's occurred again and again with nested models in my experience, that you have to find good bounds to put for these parameters. And these bounds are then put in your model estimation procedure, for instance, in your optimizer or your MCMC sample. Cool. So part 1, model recovery. Part 2, parameter recovery. Okay. So parameters return recovery. Here, the goal is to determine if their parameters are corresponding to distinct and behaviorally specific phenomena. Okay. And so we can either here use our participant parameter estimates or some a priori guess to simulate data along this x-axis. And then we're going to then fit our models again, and we can plot the corresponding estimate on the y-axis, right? So the ideal situation here is that we want to get really strongly correlated parameters, right? So here we have a situation where we're quite confident that that alpha that we put into the modeling procedure will also correspond to alpha we get back out. Okay. This is slightly less good for beta, but I think this was kind of a relatively simple abandoned task. And I think Shinsuke's talk yesterday also mentioned or hinted at some of the kind of limitations of parameter recovery for these types of simple learning models. Okay. So I think these are far from perfect or maybe good enough in many situations, but I think for many interesting problems, it's also you might also want slightly better recovery. Okay. You might also want to kind of go a bit further and do kind of something I've called counterfactual parameter recovery, where you can maybe systematically vary the simulating parameters across a range of values to see the entire hypothesis-based recovers, right? So rather than only using your parameter estimates from participants, you might also kind of inject some more noise into the parameters that you're estimating and then see if they still recover. That kind of maybe provides a bit of a higher standard for robustness. In the code notebook, you also have an example of recovery. It's a small data set of simulated data for a simple Q-learning agent. And here we see we have relatively strong recovery for our alpha parameters, so R.959. But the beta parameter maybe is a bit weaker. You have one kind of outlier here, right? I think this is probably also can be quickly resolved by kind of improving the optimizer that we're using, right? So I think I just a very simple kind of gradient descent method. And with better optimization, we might get a better estimate for that beta parameter. But otherwise, it's not too bad. So any questions here so far about parameter recovery, model recovery? Let's move on. So beyond just these kind of goodness of fits, right? This always tell the full story. Sometimes we're maybe capturing kind of like task adjacent or task orthogonal aspects of human stochasticity and choice behavior, right? When we design experiments, we're really trying to understand something kind of specific about maybe, hey, something normative of performance, right? Something normative about choices, right? What's the interesting part about behavior? And so here sometimes an important check is to see that the models can actually reproduce important patterns of human behavior. And this is proposed in this great text paper by Stefano Palminteri, where they were able to kind of falsify one set of models that kind of were invariant to these kind of and choice variability to kind of the sequence length, whereas their winning model was able to kind of capture that, right? So as the sequence length increased, Patterson had greater choice variability, the model also captures that. And so this type of falsification using model simulation is also a really important tool to use to make sure that your model is actually capturing kind of key parts of behavior. And maybe capturing differences across different populations or different experimental manipulations. Here are some data where we had human learning curves in these gray lines for people from the ages of 5 to 55, and across different age groups, this kind of black line was providing relatively good fits to human behavior. So there's still maybe some room for improvements, but this full model was providing better kind of characterizations of those learning curves than alternative models. Cool. So here I'm going to try to kind of summarize by kind of all the tutorials together by providing something like a general recipe for cognitive modeling. So this isn't kind of a fixed set of step-by-step instructions, right? Every one of you are working on different types of problems, different types of tasks. So there's not going to be one prescription, right? But rather the real kind of world that you're all in is something maybe more kind of like this illustrated by the kind of adaptive set of principles, like in the famous cooking competition Iron Chef, right? Where all of you are faced with some sort of surprise ingredients, right? Some surprise challenge to incorporate things like I think apples, zucchini or squash, any number of ingredients that you're modeling in your specific topic, right? So here we're going to give you an adaptive set of principles. So this general recipe is that maybe one, really try to approach modeling in a theory-driven way. Come up with clear theory-driven hypotheses and turn them into models, right? The advantages of the models is that they provide kind of explicit commitments to the computational processes involved, rather than vague verbal theories that one day can mean one thing, another day can mean something else. 2, determine how you're going to estimate the model parameters and perform model comparison. Are you going to use maximum likelihood estimation or Bayesian methods, right? Are you going to use model comparison based on BIC, AIC, cross-validation, etc.? And then you can already at this point test if your modeling framework is robust, okay? Here you can already, before you even collecting any data, right? You only have like the kind of the sketch of your experiments. You can already implement that in your simulations. Simulate your data, perform model recovery, perform parameter recovery. Is your task sufficient for these to recover? If not, maybe rethink your framework. Maybe you need to switch to Bayesian methods. Maybe you need to expand the amount of data that you're going to collect in your experiments. Maybe you're going to just rethink the design of your experimental manipulations because they don't provide distinct enough kind of manipulations on behavior to kind of be observed in the model outcomes or the parameters that you'll define for these two populations, right? So here's a situation where already before you've collected the data and did the costly data collection, you can already have a better kind of chance at getting results that are publishable. So we're not shooting blindly, but rather we're taking aim and using models as a tool to help us kind of make more precise scientific hypotheses and scientific approaches. At this point, then you can collect your data. From this, you can analyze the results by simply kind of copying and pasting. It's changing one line where you're taking the CSV file from your simulated data and replacing with your actual Python data, right? You've already done all the work here, and then this part is actually relatively simple. Here you will still, though, often want to test if recoverability still works with your human participants, right? Your initial guesses in the prior distribution of your parameters that you're simulating the models might have been inaccurate, and you might still want to kind of run these recoverability tests to confirm that indeed in the kind of the parameter distribution in which your participants are living in, that you're able to get strong recoverability. And here you might also want to kind of check that, hey, we have now our behavioral patterns. Can we also reproduce them in our model simulations, right? Is kind of or have you falsified some alternative models as well? So ultimately, this is just kind of an adaptive general recipe. And when it comes to modeling, ultimately your goal is to try to figure out what choices can you make that you can justify to yourself and to your reviewers. Okay, so I just want to then conclude with some recommended readings for kind of digging more into this, and maybe also point out that me and Wataru have been writing a tutorial paper for some time, and I think we're really hoping to kind of get this out quite soon. So maybe keep an eye out for that as well, that captures all these principles. So thank you for your time, and then we have a bunch of time for some discussion and questions. So please.